Hello, good morning, good afternoon, and good evening from wherever you're logging in today. Welcome to this week's Smart Seminar series. It's my pleasure to introduce Tapas for the presentation today. Tapas Tripura is a PhD researcher in applied mechanics at IIT Delhi who specializes in computational mechanics and scientific machine learning. His work focuses on data-driven discovery of physical systems, operator learning, scientific foundation models, reinforcement learning for intelligent control, and the list is endless. He has developed and has contributed extensively. Few of his notable contributions are Wavelet neural operator, a Lagrangian-based framework for discovering governing equations from data, the neural compositional wavelet operator, and many more. Out of this, he would be presenting today to us the neural combinatorial wavelet neural operator and would like to share his insights with us. Now, with that brief introduction, please join me in welcoming him for today's seminar. Thank you. It's all yours, Tapas.
Yeah, thank you for this brief introduction. I'm again really glad to have the opportunity to again present a part of my doctoral thesis in this SMaRT seminar series. So today I'll talk about NCWNO, which stands for Neural Combinatorial Wavelet Neural Operator. So it is a scientific foundation model, so mainly developed from our group for learning solution operators of multiple PDEs simultaneously, right? So now before delving into this, the framework of this NCWNO, I would like to set up the stage for the audiences. So in scientific computing, we are mostly involved in predicting or solving the governing physics of the underlying system, which is nothing but a mathematical model of the physics of the governing physical system. Now, in classical sense, these are usually the solutions are obtained using certain numerical solvers. Now, since this is a scientific community, it is like the community knows that these classical solvers are computationally slow. So in scientific explorations, where we need multiple or repeated runs of such models, so these classical numerical solvers, they becomes a bottleneck. So further, applications like reinforcement learning and the reliability analysis, where we need real-time predictions. So in such cases, also these numerical solvers becomes a bottleneck due to their high computational or intensive computational time. So in recent times, these deep learning based emulators have come up, which tries to approximate the mapping between input and solution through composition of certain functions. Now, neural operator takes this to another further, where instead of learning a vectors to vector mapping, we try to approximate the underlying solution operator, which is nothing but mathematically termed as a mapping of infinite dimensional mapping between two function spaces. So now there are many frameworks have been proposed. So one of the most popular approaches is this integral kernel-based neural operator, where given a linear PD, we can find the solution using this Green's by convoluting the Green's function with the source function. Now, finding this Green's function for a very complex geometry or high dimensional problem becomes very intractable due to the complexity in computing the homogeneous solutions or satisfying continuity. So now that Lee et al. In this FNO, they proposed why not learn this Green's function from data. So they proposed an integral kernel framework where they learn the Green's function from data and then use the Green's function use the Green's function in the convolution between the input and the Green's kernel in the integral layer. So now again, since Green's function is mathematically only valid for linear, this is generalized using nonlinear operators. Now here nonlinear operator is similar to nonlinear activation functions. Since here the framework is nonlinear operator, so I would like to call the nonlinear activation functions as neural operator. Now this is further generalized to nonlinear Hammerstein type integral by adding a linear term, is represented by this L. So if you are to look in a, like overall, so given the previous input Vt, so the and the whole like predicting the output involves an Wavelet integral block, which is represented by this integral kernel, and a skip connection. The outputs are then summed up, and an activation function sigma is applied over the output to finally obtain the updated solution. So now in Wavelet integral block, the idea is to perform this convolution in Wavelet space instead of the physical space, because there are many advantages are there. For example, one of the example is the features in the Wavelet space becomes localized. So learning becomes much easier. So now what happens in Wavelet integral block, we take an Wavelet basis function, and given the Wavelet basis for the like given input, we perform an Wavelet decomposition on the input. So which yields and like an approximate coefficient and a detailed coefficient for the input function. Now we recursively perform this Wavelet decomposition to obtain our all sets of these approximate and detailed coefficients. Now then in the Wavelet space, we define our this network kernels, and we perform this convolution. And once the convolution is performed, we finally perform inverse Wavelet decomposition on the convert output to get back to reach back to the physical space. Finally, we add the skip connection and apply an nonlinear activation operator to get our output. Now, since this kind of this iteration is not enough, we compose multiple such iterations to finally obtain our this overall obligatory operator framework. Now, now in this stage, like this obligatory operator can only learn the solution operator of a single PD. Now, the training and multiple task-specific these Wavelet neural operators becomes a resource-intensive task, which not only demands energy but also like demands high computational time and resources. So towards that, we want to develop a unified single framework, operator framework, which can learn the solution of multiple PDs. Now towards that, we'll take our motivation from our cognitive science, where our brain tries to learn new things by connecting by establishing connections between different parts of the brain. So in order to say that, so just look at this two network. So basically, it represents a 6-noded network, which is trained on task A and task B. Now, so for this two network, we can ensemble these networks in their node level. That is to say, by in the new that ensemble network, basically represented this the third network. So we can at the same node level, we can select in that name that feature from the previous two networks, and possibly by we can now if now if we could ensemble these two networks which were trained on this task A and task B, and obtain our this new network, then we can possibly expect that the global ensemble will work on tasks beyond which it was actually trained. So that is to say, if I have trained two networks, so in this case, this 6-noded network trained on these two tasks has a potential to generalize to 2 to the power 6 pseudo tasks. Now, and it can be further improved by not only choosing a node feature from the previously learned task, but creating a mixture of the features. So instead of directly choosing only the particular node. So this mixture is represented in this the fourth figure using these color gradients. So with this motivation, we want to create this kind of modularity in our Wavelet neural, that neural combinatorial Wavelet neural operator framework. So in the previous that WNO frame of that architecture, our this wavelet integral block contains only one this wavelet kernel integration followed by a skip connection. Now instead of using a single wavelet kernel integration block, we introduce multiple such integral blocks parameterized by different wavelet basis functions, and we call them as a wavelet expert block. Since each of these WIB uses a different wavelet basis with different support width, so they extract different multi-scale features from the input. So now to understand what it happens, so how the combinatorial learning happens here, the input V, or the first input, is passed to these local wavelet integral blocks, and this wavelet integral blocks produces the some output. Now these outputs are ensemble in their channel level. So not all the channels of this the outputs from these wavelet integral blocks will be mixed like in a similar way. They will have their different ensembling. So as you can see, this ensembling is represented in a gradient, and each gradient is different from different channels. Now, how these channels will be ensembled? They will be ensembled using certain probabilities. For like, we'll assign certain probability for each of these channels. Now, this probability is estimated from a probability gate. Now, this probability gate takes the PD information, the PD level, basically which PD we want to trying to solve, and the context information, that is the input as well. So now finally, after ensemble, we add the that skip information, and we apply a nonlinear operator to get our that updated output. Now now here, since these wavelet integral blocks they are inherently discretization invariant due to the kernel integration, they preserve the discretization invariance property. Now to also introduce this probability, that discretization invariance property, that property to the probability gate, we design it as a composite network. So what happens for the PD level L, we pass the L to throw in encoding network. So that is nothing but an 4 or 5 layer MLP. Now this is very this gives this have the discretization invariant property, because this L won't change. It is a scalar. So for whether the input field increases or decreases, this L is always going to remain scalar. So this MLP doesn't create a problem. Now the problem happens in the context information, because that is where the resolution will increase and decrease. So what we do, we introduce a 2 or 3 layer this wavelet integral block, which encodes the context information to a latent space. Now, in the latent space, we flatten the spatial information, keeping the channels remain same, keeping the channels remain intact. Now, similarly, this the encoded level information, we repeat it along the channel, and finally we concatenate them. After concatenation, we finally pass it through a feed-forward network, which is again an MLP. And then finally, at the end, we apply softmax function, which estimates the probabilities across these channels. So in like how the channels we will get ensemble differs for across the channels. Basically, not all the channel will be ensemble in a similar way. So now to summarize it, so we have a PDL, some like associated initial condition or complex geometry from what for which we want to predict the solution and the associated grid. And finally, so in the beginning, we concatenate this input parameter and the grid and pass it through a lifting transformation, which lifts the input to a high dimensional space, which also we term as a context information. And then we pass it through this expert blocks where the probabilities are measured using this linear embedding and this context information. Finally, by stacking these multiple expert blocks, we obtain our this solution, right? So now to test its effectiveness, we considered 6 1D time dependent PDs and 6 2D time dependent PDs. So for all of the PDs, we varied the initial field. So those fields are generated from this RBF kernel. Now for the Burger's equation, basically 1D Burger's equation, to keep the shock behavior, we sampled the initial field from this sign field. The initial condition is this sign field, right? So now each of these PD has 1500 training samples and 100 test samples, and the spatial resolution, the training spatial resolution for the 1D PDs are kept as 256 and 2D PDs are kept as 64/64. Now here we aim to perform two tasks. The first task is in context learning of multiple PDs, where using a single NCWNO model, we aim to learn the solution operators of the 1D or 2D tasks. By learning the multiple tasks, we aim to establish that this NCWNO can indeed be used as a foundation model to instantiate a foundation model. Now, if the first task is possible using NCWNO, then we perform the second task. Where using the first foundation model, we aim to learn new PDs without catastrophic forgetting of the solution operator of that foundation tasks. That's what is represented in this this figure, this bottom right corner figure. So before proceeding to the results, I would like to let us look at the distribution, how the similarity of this data. So to measure the similarity between this data, I have actually considered these three measures. The first one is the cosine similarity, which measures the that geometric similarity between the data sets. So one being the exactly similar and 0 being the very different task. Then we have this normalized scale divergence, where again 0 means there is a perfect, the tasks are overlap each other, and 1 means they are completely different. Then in the third measure, we have this mutual information, which measure this statistical dependency. 0 means there is no statistical dependence, and more higher the value, it means more dependence between the data set. So now here we have this the prediction results of this 1D PDs. So we have this 6 1D PD here, and for each PD, the temporal snapshots at 4 different instances are also shown here in this graph. You can see the predicted solutions, which is represented using this blue dash, or exactly, not exactly, but almost exactly approximates the truth represented by this solid red graph. Right. So now proceeding to this 2D example, here also you see all of these PDs almost have their different their fields, different fields, but still the one single NCWNO is able to predict all the PDs simultaneously. Now, we have also compared it with two such in context learning framework. One is this icon, which at that time only supported 1D PDs. So this is the icon is a 31 million parameter model, and our 1D NCWNO was 41 million parameter model. So like you can see, our NCWNO in the given tasks clearly outperform this icon. Now another this 2D model is there, which is multiple physics pre-training, this MPP. Now it had some three models, so we choose the lowest, the smallest, and the biggest model, which is represented by this avid V, the smallest, and avid L, which is the largest model. The smallest model had 116 million parameter. The largest model had 409 million parameter. Compared to both of the frameworks, our NCW had around 92 million parameters. Now, despite being smaller than this 2D MPP models, you will see in these values in the table that our NCW is much better, performs much better than these MPP models. Now, even if you compare this training time also over all the tasks, this our NCWNO and is like quite it takes very less training time as compared to this 1D icon and 2D MPP models. Now, coming to the zero shot capability. So remember our 1D NCWNO was trained on 256 grid. So here you see in the first column the subfigures A and B. Even in the that when the that pre-trained model was predicted on a 512 grid or 128 grid without pre-training, without fine-tuning, our this pre-trained NCWNO like preserves its accuracy to almost above 95%. Similarly, if you look at the second column, basically B and D, our NCWNO model, 2D NCWNO model was trained on 64x64 grid, and here we tried to test on either 128 cross 128 or 32 cross 32 grid. So you'll see here also the performance degrades, but it still remains beyond 90%. The accuracy remains beyond 90%. Yeah. Then we also tried exploring the capability or generalization to out of distribution initial conditions. So where like in the random, like just to highlight, in the training, our initial condition was generated for different different initial conditions which were generated using a single RBF kernel, basically where the sigma and L parameters were fixed. But in this prediction stage, our the parameters of that RBF kernel itself, it was varying. So even in that case also, our this pre-trained NCWNO kept its performance around or more than this 95%. So now talking about this training and inference cost. So when our this foundation task, it so maybe I'll come to this later. So now we also tried. Okay, I'll also come in here later. So now in the next stage, like in the task 2, we aim to investigate whether this NCWNO can be pre-trained on a set of tasks and then can be fine-tuned to new tasks without catastrophic forgetting. So here we have this pre-trained NCWNO model. So during fine-tuning stage, what we do? We fix the parameters of the this MLP and this expert blocks, and only update the parameters of this probability gate. So right here, and we store only the parameters of this probability gate, which constitutes around 1% of the total network size. So which is very much effective than training and neural operator from scratch. Now let us see how the results are. So now here in the 1D continuous NCWNO model, we train the foundation model on Alenkern, Nagu, and wave equation. Then we fine tune on Burger's advection and heat equation. Now, since the foundation model is pre-trained on Alenkern, Nagu, and wave equation, you can see the accuracy almost remains above 95%. However, since it is not pre-trained on Burger's advection or heat, or neither yet fine-tuned, their performance on this Burger's advection and heat equation remains very poor. Now, when we fine-tuned it on this Burger's equation, you will see the accuracy has improved to above this 95%. But like in the normal state, like normal this neural operator framework will expect the model to forget the solution operator of the foundation task, that is this Alenkern, Nagu, and wave equation. But in this case, when we test, we see that the performance on this foundation tasks also remains same. So basically, we have almost zero catastrophic forgetting. But since it is not pre-trained on advection and heat, you will see the accuracy is still poor. So again, when we adapt the sequential model to the advection equation, you will see the accuracy not only improves for the advection equation, not only improves above this 95%, but the accuracy again remains same in the previous tasks. Now, similarly, when we adapt to the heat equation, you see we see that the adapted model has accuracy above 95% in all the tasks. Similar phenomena we see in this 2D model, where we pre-train our that foundation model in the Navier-Stokes, Alenkern, and Burgers equation. Obviously, since it is trained on this 3 equation, their inference also like has very high accuracy on these 3 tasks, but on the other remaining tasks, it has a very poor accuracy. But when we fine-tune it on the advection, the accuracy improves while maintaining the accuracy intact for the foundation tasks. Similarly, when we perform fine-tune on the Nagum equation, you can see the similar phenomena, and so do for the heat equation. Now, I'll skip it here. So now we also checked its performance against certain task-specific operators. So you'll see we have considered 6 tasks. So this Darcy are time-independent equations. This 1D Alenkern and Kuromoto-Shibasinski has the 1D time-dependent equations, and 2D Navier-Stokes and this 2D Nagumo are the 2D time-dependent equations. So in all these 6 tasks, you will see this our NCWNO consistently outperform these other frameworks. Now coming to the training cost and training and inference cost, you will see the foundation tasks. We trained the foundation tasks for 200 epochs at a batch size of 20, which amounts to 75 iterations for each epoch. So in total, this the whole training time takes around 1038 minute for per epoch for this 1D task and 2357 for the 2D tasks. Whereas in sequential tasks, we use only 100 epochs and 500 samples at a batch size of 50. So we essentially at per epoch we use only 10 iterations, 10 model updates. So that's why this time reduces to 65 minutes for 1D continual model and 513 minutes for the 2D continual model. So once they are trained, you will see their inference time is very less. So 0.16 to predict the entire trajectory for the 1D task and 1.3 second to predict the entire trajectory for 2D tasks. Now, we also did ablation study over the number of these experts. So you will see the lesser the number of this expert, we have the lesser number of parameters, and higher experts means the higher parameters. So as we increase the number of parameters, we see an increase in the or decrease in the L2 error, relative L2 error. But after certain number of these experts, say in this case, this after 10, or this that error almost saturates. Now we have, apart from beyond this beyond these tasks, we have also tried exploring 3D, the like applicability of this NCWNO on 3D tasks. So here, given this MRI image fields, we aim to estimate the corresponding stiffness field, which is popularly like termed as the medical elastography. So here we again have this lifting transformation and an expert block, where now instead of 2D we have this 3D wavelet integral blocks. So now by stacking these multiple wavelet integral blocks, where we actually, by stacking these multiple wavelet integral blocks, we are able to estimate this elasticity. Now, why here this expert block is needed? So because here this medical elastography, these elastography images are like collected for different frequency of this MRI imaging. So by training a single model, we were able to predict the corresponding elasticity elasticity fields for different frequency information. So now here is the prediction results. So as you can see here, at different hertz, that is 30, 50, and 70 hertz, the single model was able to approximate the ground truth with very accuracy. And this is a very like real image, real patient data. So even in this real patient data, when we check this correlation, you will see the predictions and the true value almost they they overlap each other. Now again, since this is a like basically a segmentation kind of task, we also compared it with existing frameworks. So one is the deep CNN, one is the 3D PFSR, and one is 3D deep left version 3+. So in this comparison, we see that this framework, it performs much better than this existing frameworks. Now, since this is a real image, so it becomes important to investigate its like sensitiveness to this measurement noise. So that's why we tried to perform a case study. Here we see this 30 hertz, this model suffers more than this 50 and 70 hertz like this data. So now we have now at this in this all this framework, we have considered the data to be in a uniform grid, and all the data to come from a single modality, that is either all brain and similar data structure, all the thing. Now in in this new work, which is still currently going on, we have considered three dataset of multimodality, and all the data in a point cloud. So we don't have a uniform grid. So in the first data is the first problem is predicting this Navier-Stokes flow over this band pipe, where we have a initial velocity which is scalar, and we aim to predict these three fields, Vx, Vy, and P. Then in the second data, we aim to learn this dose field rate from this neutron counts placed over 7 locations over the world. So here the input has a tensor shape of 7 cross 12, but an output is a single field having a like a points of point cloud of size 6,000 65,341. And in the third data set, we aim to predict the stress field, the scalar stress field, given the history, the temporal history of this load. So the input data, there are 101 temporal points, and output is the 3060 size, that point 3060 points in the point cloud. So now, since this is still undergoing, so that I have not presented this framework, but there are certain these results you can go and play with the in this website. So okay, maybe I think yeah. So this is a collaboration work, this Martian slab. I forgot actually. So you can search this NGROC NCWNO. So you'll find the website in the Google, and you can see how this a single NCWNO model was able to learn the fields from all the three multimodality data, and you can also see the accuracies over for each of the keys. And yeah, I hope this is it. Yeah, thank you. And if this work excites you, you can find the original NCWNO code from this GitHub repository. Yeah, with
Thank
that,
you, Taposh.
I'll conclude my presentation.
Thank you, Taposh. This was wonderful. Excellent work, as always. So I'll open the floor for questions from the audience.
Hello, Tapas. I'm Prashant.
Yes.
Can you go to your architecture of the model, your foundation model? Yeah, a little bit below. The next one, the down one. Yeah, this one. So I had a very basic doubt. So what is the input in your model and what is the output? Like, are you giving the solution at t equal to 0 and are you predicting the solution at some time t equal to t, or like this is the basic confusion I have. Then I can give, then I can ask the other question.
Okay. Yeah. So so this is a at this stage, this is a time independent framework. Just so at A, we give our this initial condition. Say if you consider 2D Navier-Stokes equation, or say okay, let's consider a time independent equation. So if it is a Darcy, say we want to predict pressure to permeability field or permeability field to pressure field. So A is my permeability field, X is the grid over which I want to predict, L will be, say, for this case, since it is only one PD, you can put 0 or 1, and this output you will be your solution, that the pressure field. Now in a 2D in a time dependent problem, our A will have the in this case I have considered previous 10 steps of the solution, the temporal snapshots, and so A is my previous 10 temporal snapshots, X is the solution grid, L is again some number, and U is the say that 11th time step, the snapshot at the 11th 11th time step. Now this is got, you have got given the 10 snapshots, 0 to 1 to 10, you have got 11th step. Now you again take the 11 and stack it. Now given 2 to 11, you again predict the 12th one. So that's how it is an auto-regressive framework.
Okay. So yeah, now my original question is like, you have already studied, you might have studied the basic CNN networks like Google Net or VGG, right?
No.
Like, no. Okay. So if you see that the diversity of data that they use for the classification, like they have, let's say they are doing the classification of 1,000 different kind of data sets. For each data set, for each kind of data set, they have 100 data, let's say. And still they have the 100 million parameters. And in that case, do you see that this network has that kind of diverse data and still the network parameters are 100 million? No, because the question basically comes from like I have not been able to understand the neural operator clearly, like the motive. So that's why I asked this question, because the formation of this network looks very much similar to kind of VGG network or Google Net network. So that's why I asked this question. Yeah.
Okay, so I didn't see the Google Net and all. So the tasks you were referring to, the classification, for us it is a regression. And why is the neural operator? So in basic neural network, your input and output, that dimension is fixed. So basically, if you train on an image of 256 cross 256, even in the testing, you have to use that size of image. But in neural operator, we relax that. So even if your input is, even if your model is trained on 256 cross 256 grid, during inference, you can use theoretically any like resolution. So it could be 128 cross 128 or 512 cross 512. So that's the main motivation for using a neural operator. And the data set we have used, like we have, like for us it is since a time dependent equation, like it's that, so even training for the 6 was becoming very heavy, so that's why we couldn't explore that 100 different types of examples. But what I can motive, like I can see is that in the 6 PDs, you'll see each of them has a different like solution field. They are not same. So for example, Burgess, it have a shock kind of behavior. This wave equation, you'll see it is like wavy field. And in this Alenkon, you'll see there are certain like steps, like step jumps. So this, all the 6 PDs have kind of like quite 6 different diverse uh, feature. So now, like whether it will work for that 1,000 different types of tasks, that I cannot say at this moment.
Okay. Okay. Thank you. I understood. The one of the motivation that you are telling is basically like prediction at the different dimensions, like different grids. That
That is, sorry for interrupting you. That
yeah.
is for only one Wavelet neural operator, or one DeepNet, or one FNO, or one this transformer architecture. But see now, if you train for these 6 PDs, you need to train 6 such neural operator. Now training for each of them from a scratch requires a like again repeated energy, repeated number, like 6 times the energy, and like time, that computational resources. Here in this Combinatorial, this NCWNO framework, we go one step more. So where we learn the solution operator of all the 6 PDs together. So
Okay.
even in inference, you don't need a single, you don't need 6 different models. You don't have to do the bookkeeping, which model is for which PD. You just use simple one NCWNO, and you just like predict it for advection, Nagumo, Alenkon, Burgess, or heat wave, or any. If you train it for maybe more number of PD, you would be able to predict for more number of PDs using this single NCWNO model. And another also advantage, here we have seen that, like even in this, when we train it for only these 3 PDs, basically that Alenkon and Nagumo wave, it can also be fine-tuned to new PDs like this Burgess, advection, and heat. So it's
Yeah.
like a foundation model. Yeah.
Yeah, got it. While we were discussing, I also got the point that in any CNN, we don't care much about the accuracy. We only care about classification. At the end, if our classification is correct, we are fine with it. But here, the accuracy is very important for us. So it might be the case that even though we have lot number of parameters, I mean, even though we have a very small number of data set, because we need accuracy, we might need larger parameter for a small data set. I mean, this is what I am concluding. And yeah, the last point you explained, like, because this network is able to learn the new physics without losing the previous physics, that is also great. Yeah, thank you.
Yeah, thank you.
Thank you, Prashant. That was a good question. Do we have more questions from the audience? Okay, if not, Tapush, I have a couple of questions.
Yeah, sure.
So, you showed the 1D and the 2D examples. Did you train the 1D and the 2D simultaneously in your NCWNO model?
No. Not in this framework. Not in this result.
Okay.
But the very last one where I've shown you the multimodal one, yeah, there it is both like 1D, 2D trained simultaneously.
Okay, then how are you indicating to the model how many wavelet decomposition they have to do? Because if you are in a 2D setup, you need to do wavelet decomposition on a 2D domain. If you are in a 1D, you need to do it only on 1D. How are you handling that part?
Okay, the last framework. So basically, there we use a graph to like all project them to a like standard latent space. So in that latent space, it becomes kind of
Ah,
same for all.
I see. I see. So it's an affine transformation that you're carrying out.
Correct.
Okay. Okay. And apart from autoregressive, are you thinking in terms of doing a full rollout?
In autoregressive,
I mean, the
uh,
question is basically like why autoregressive? Because we know there are a lot of disadvantage to autoregressive models.
so like 3D, in 3D also we can do where if it is a 2D problem we can do 3D where the third axis will be the time. So yeah, that is one thing we can do in the
It was more philosophical, Taposh. Like, why did you choose to do autoregressive? Is
so
there any?
basically we just wanted to follow our the previous work on WNO and plus in this reinforcement learning framework where I use this. So basically, I wanted in a real time, not all things together. So I just
I see.
wanted one step at a time.
Okay, okay, okay. It was a requirement then. Okay, I see. Okay, that was wonderful. Uh, if there are no more questions, we can probably call it a day today. Thank you, everyone. Thank you, Taposh, for giving us this wonderful presentation. Thank you, everyone, for tuning in today. We'll again meet next week at the same time. Thank you.
Thank you.